Oops. Well, that's not working. Okay. Okay. This particular slide isn't on your notes, but it's something you should have been able to recreate had I asked it. And let me just summarize it for you. When we're looking at issues related to calculating flood discharge of different recurrence intervals, and when we're using stream flow data, as we did in the example I ended with last time, there are certain assumptions that we've made. One, that there are no climatic trends. Well, we've already discussed the problem related to that. That events are random and independent. This is a pretty fundamental assumption of hydrologic events, and that is that last year's rain, or rather this year's rain, has no memory of last year's rain or yesterday's rain. Where that breaks down is really where we're getting into weather or climate trends again. We do know that, for example, we have El Nino, La Nina cycles. So that can affect, if you like, a memory. The storms, remember, they're in an El Nino cycle, if you like. And so the frequency distribution there might be a little different. Clearly, as we've talked about, there's no watershed changes. That'd be the effect of urbanization. And of course, if there are, we need to take that into account. Something I haven't talked about is called mixed populations. And that is, the assumption is that all the floods are the same type. Now, what I mean by that is that the flooding is of the same origin. So, for example, it's all due to rainfall. Now, in fact, if we were in other parts of the country, we might find flood records on a particular stretch that in some cases due to rainfall, in some cases due to snowmelt. And so there you've got a mixture of two different conditions, and in fact you would have to separate those out. You'd have to look at the flood frequency distribution of, let's say, snowmelt flooding versus the flood frequency distribution of, let's say, rainfall-induced flooding. Also, that measurements are small and random. That might seem to be obvious, but there are situations where, as you look at the flood records, they're not always as precise and accurate as you would like. When I was working up on the Yukon Delta, or Yukon River rather, I was looking at old records trying to figure out flood frequency, and I'm going through the notes, and there's a 2-week gap. Gone salmon fishing, no records. Okay, so you are dealing with both instrument and human foibles that can affect the reliability of the measurements. Okay, so we talked about using streamflow data and graph fitting curves, that is extrapolating that to with the recurrence interval. Okay. With the recurrence interval formula that I use. And that is actually probably the only formula that I'll ask you to remember. But there are also math fitting curves using the same sets of data. And so here we're actually trying to predict the frequency distribution as an equation and then use, based on the measured discharges, and then use that equation to extrapolate. Remember, we talked about the fact that we rarely have 99 years of record. So we rarely actually have a dot that says 100-year flood. On the other hand, we can extrapolate trends. And so using this particular formula or a formula like this, we can extrapolate those trends. This particular formula is one, I didn't seem to copy it, this called a log Pearson type 3 curve. You don't need to remember that, but it's a specific distribution. We're all familiar with the Gaussian distribution, bell-shaped curve. Rainfall events aren't like that. They tend to be skewed. They tend to be stretched out on the high end, with kind of the most common being fairly low frequencies. So we need to know things about the distribution of that curve. And so what we're looking at is the mean distribution, the standard deviation of the distribution, and some measure of the skewness of that distribution. And when we know that, then we can use this equation and we can plug it in and extrapolate out, and also look at the variability. Okay. So one of the things that we would see is not only a line, but confidence limits, say looking within 1 or 2 standard deviations. Okay, so these are useful pieces of information. Now, the third type of technique comes mainly when we're dealing with ungauged basins. I showed a map that shows there's really a lot of gauging stations, but not really compared to the number of little watersheds that we might be interested in. Okay, and so that requires us to regionalize our data. And so there's a variety of ways of doing it, but the most common way is to try to do some kind of a multiple regression analysis where we're trying to find things in common between the gauged and ungauged basin, and that that are important towards determining the discharge. Okay. So things like drainage area, certainly, but precipitation intensity, slope, relief, things like that are what we would use, and then we'd develop empirical coefficients to try to generalize that. So we've got discharge is a function of or proportional to your variables to some component. Okay, and so this again is just a different multiple linear regression system where you're looking at stream flow characteristics and are a function of basin characteristics. Okay, this is an example. We're looking at the discharge of a P%, maybe the discharge of a 100-year flood, is equal to some coefficient times the drainage area raised to some function. Now that would be the simplest of one, because it says in this particular area the only thing that drainage area is the variable, and what we're looking, or better said, given drainage area, we can use the power function and some coefficient as proportionality to predict the discharge. Okay. Usually they're not that simple, but that would be a simplistic way of looking at it. This is another type of regionalization. We use this sum. It's called the rational method. And it says the peak runoff is a function of C times I times A. Okay, well, A is the area. I is the precipitation intensity for the time of concentration. And I'll define time of concentration later, but recognize precipitation intensity varies over different intervals. C is a coefficient that you would look up, and it would be based on the type of land use and soil type. So if you got a drainage area that consists of, let's say, maybe 2 soil types and maybe 3 different land uses, you could look at the relative percent of that. You could get a composite C, determine the time of concentration, determine the rainfall intensity, drainage area, and you have the discharge for that particular probability. Clearly, that is most useful for a small drainage basin. Okay. Here's an example of a broader way we usually do that. And so the first thing we've got to ask ourselves is, what is the rainfall, rainfall event that we want to predict the flooding from? Well, there's first of all the duration. So this particular idea is looking at a 24-hour duration. Okay. The second is at some probability. Let's say the 1% rainfall over 24 hours. Okay. In fact, we have graphs and tables for all of these for specific regions. So if we were interested in Houston, well, actually, if we're interested in Harris County, we might have to look at 3 different regions, depending on how rainfall differs from Katy, say, down to Baytown. But then here are all the various examples of variables that we might look at. Okay. And again, I don't want you to memorize this, but recognize the types of variables that we would be trying to correlate with rainfall. And when we do that, this is the kind of map we get. Okay. The color trends are annual exceedance probabilities. Now, for what kind of rain? Well, it's a 24-hour rain. So we've got, for Boulder, sitting here, Boulder, Colorado, we're looking at a more than 1,000-year probability, more than 1,000 probabilities. Okay, one divided by 1,000. So that would arguably be the 1,000-year rain. Okay, up in here, it's the 10% rain. So just as we have in seismic hazards, we've got a map that takes into account maybe the acceleration for a particular recurrence interval or exceedance probability. These are the kind of maps we'll be doing here. And I'd like you to look at this map and think about how this map is made and compare it with the seismic risk map, how those maps are made and how they have a similar approach, but a little bit of how they differ. So that would be a compare and contrast study guide question. Okay. Now, if we look at those drainage area variables, we basically take a topographic map or a digital elevation model, and we have to start from a point, of course, like all drainage areas, and we'd look at things like the main channel length, the main channel slope. We'd also look at shape of the channel. Now, you might think shape shouldn't make a big difference, but it actually does, because it affects the rate at which different amounts of runoff reach the outlet of interest. So in this particular example with an elongated basin, the peak discharge arrives pretty early and drains pretty quickly. On the other hand, if we have a kind of an equant basin, kind of roundish, then the rainfall, it runs off over a longer period of time, and so we get both an increased time lag and we get a decreased peak discharge. Okay, so each of these basins are the same area, and each of those rains are the same rain, but they create three very different hydrographs, three very different hazards with respect to flooding. Okay. Now here's looking at the same shape but a different size. What we're doing is we increase drainage area. We are both increasing the peak discharge but also increasing the duration over which that flood event occurs. And it's not just the peak to flood or lag time, but it's also how broadly the floodwaters are spread out. So if we're looking at a little urban basin like I don't know, Buffalo Speedway, Buffalo Bio, we would expect very small time lag but fairly high peak. But if we took the Mississippi River drainage basin, we would expect a much longer delayed time lag, but of course, because of the volume, it would be a much larger peak as well. Okay. Increasingly, we're using computer-generated models. So really, the state of the art now is to have a stream flow model that basically takes rainfall to runoff. Okay. Particularly the stream flow data, the first that I talked about, we needed gauging data. And then we recognize that we don't always have gauging data, so we try to extrapolate. But the reality is we know a lot about how water works, and we know a fair amount about rainfall. And so if we can take the rainfall we're interested in, remember the 24-hour rainfall, and look at different exceedance probabilities, instead of simply trying to regionalize, we could actually work it out for a particular basin. Okay. Now, we'd have to know the detailed topography of that basin, because we're literally going to take the water from the watershed divide and bring it as overland flow into gullies, into channels, and those channels into tributaries as they converge downstream to a point of interest. Okay. So, for example, here we use a digital elevation model that was derived from LIDAR data. Okay. And then we also get our rainfall data from National Weather Service. Okay, so we've got data tables. So we combine that through a model, a computer model. This particular one, there's many, is the TREM 2D model. And that model, combined with the GIS overlay, which would include not only the digital elevation map, but soils and land use, etc., allows you to generate a flood map. And this is an important advance, because what we're looking at now is not just discharge or discharge at a point, or even rainfall converted to discharge. Now we've actually routed that discharge over the whole basin. So we've gone from looking at predicting stage at one place, or better said, discharge at one place. And through a rating curve, we might be able to say stage at one place, to extrapolate it over the whole basin. And that is fundamental to our understanding of how we can create a floodplain map. Okay. Now, there's one last thing I would mention in terms of looking at flood risk, and that is probable maximum or design floods. They're two really separate things. The design flood is whatever flood it is that you feel like you need to design for based on the risks involved. So for a single-family dwelling, it would be probably a smaller flood. It would be a smaller flood than for a nuclear power plant or a dam. Okay, so we need to decide and what are we designing for? And at least at one extreme, we could take the biggest flood we can think of. Now that clearly would be for the situation where we're designing something whose failure would be catastrophic. So a dam, nuclear power plant, something along those lines. And so we could look at that one as maximum probable precipitation. And so what you say is, okay, based on historical data and everything we know about atmospheric science, what is the maximum dump of water we might expect? And if that maximum dump occurred, what would that be in terms of rainfall? And then we'll transform that into flooding. Okay, we create the maximum probable or probable maximum flood. Okay, what would that be? Well, so actually, in a lot of cases, it comes out to be close to a 500-year flood. But again, the intent here is that we are trying to use, in some cases, worldwide data, but certainly climatic data, to figure out what is the worst it could be. Now, I'm going to use, for some examples of how it's used here in Houston, examples from the Hydrology and Hydraulics Manual, or Guidance Manual from the Harris County Flood Control. Okay. The U.S. Geological Survey has different techniques. Well, actually, that's not quite true. Have different manuals. This is just an example of what goes into predicting the flooding, in this case, in an urban area like Harris County. And they use a series of models, but basically this model models the topography, it models the rainfall, and it models the runoff and subsequent flooding. Okay. Now it turns out in the Harris County area, as I had mentioned before, we actually have three regions. We kind of can think of it as southeast, central, and northwest. And there's enough variation in rainfall between, as we get closer and closer to the coast, that for our rainfall statistics, we have to decide, well, first of all, where are we? Okay, so for the rainfall, we could use historical rainfall data, and again, there's advantages and disadvantages to that. We could look at a frequency-based hypothetical storm, let's say the 100-year rainfall, or we could use the standard project storm, which is basically the same as the probable maximum storm. We're using that more general term less, and we're just focusing on the 500-year storm. Okay. When we talk about rainfall, it's not just enough to say how much fell. We need to know the duration, the intensity as a function of time, the areal distribution, how frequent that type of rainfall is, the temporal distribution, again, as I said. So all of these are things that we need to either record or assume. Okay. For runoff, we're basically looking at the rainfall excess. So we've got this rainfall that comes down. We want to know how much of it's going to run off. The excess rain, excess to whatever is lost by things like infiltration. Okay. So here is for region 3, which I think is the southeastern area, a histogram for rainfall intensity, or well, it's actually precipitation in 15-minute intervals, which you can convert in your mind as to intensity. So there is a 15-minute period where, I think it's 15, no, maybe it's a 30-minute period where you've got 2 inches of rain that's falling. Okay, so, but notice the frequency distributions: highly spiked, intense rain, short period of time. Okay, so that's what our input for our model. Now that's this, and now we have to calculate infiltration capacity in order to get that excess rainfall, the runoff. Okay. Well, what does that depend on? Again, rainfall depth and intensity we've already given. That's going to be our theoretical storm. But we need to look at the losses, and the losses include interception, remember the role of vegetation, depression storage, the little local areas that don't run off, infiltration, that's a function of soil conditions, impervious surface, antecedent moisture conditions, etc. Okay, so those are the various things we need to be able to predict. Okay. So there's a variety of ways that we can calculate the losses. We're going to focus really on 2, of which Harris County tends to use only the last. Okay, I'm going to focus on the CN loss model because it's commonly used elsewhere, and the Green and AMP loss model because that's what we use here in Harris County. The Soil Conservation Service has developed what they call a CN or curve number model. And I should add that the Soil Conservation Service really, since the Dust Bowl days of the 1930s, has been extremely interested in basically rural area runoff and erosion. So a lot of what they've done, for example, the universal soil loss equation we'll talk about later, is from the Soil Conservation Service. And again, here, no, soil type and land use. They're very interested in how runoff will vary depending on what kind of farming practice, what kind of soils that you have. Okay, so they look at cumulative precipitation, soil type, land use, antecedent moisture condition. Okay, and so what they've got is their excess rainfall is equal to the total rainfall and 2 other variables: initial loss or initial abstraction and potential maximum retention. Well, the good news is I tends to be a function of S. So we can actually say that the soil loss is equal, the excess rainfall is equal to the initial rainfall and this soil retention factor, maximum retention. Well, that turns out to be a function of the curve number, okay? And it varies from 100%, which basically says none of the water is running off, to 98%, where it's a paved area and almost everything runs off, okay? So if we know the curve number, and that's a function of land use and soil type, then we can figure out how much is lost. And so here are some examples. Let's see, maybe grasslands or pasture. Well, the first question, what condition is it in? Good condition, poor condition, and then what soil type is it? A or B or C or D. Okay? And then from that you get your curve number, and you simply apply it to the rainfall, and you get the excess. So this is for agricultural lands, this would be for urban lands, and it tells you how to use soils maps and land use maps to calculate a curve number, and from that generate excess rainfall. Okay. Now, this is just an example. Actually, I was going to go back and forth to do it, but it'll take a little too much time. But I could ask you on a homework assignment to say, okay, let's suppose that we have 1 inch of rainfall and we had woods in good condition and soil group B. Okay, well, you go for, let's see, woods, good condition, soil B, that's a curve number of 55. So you put in 55 here, and then you would generate your S, and then from that generate your piece of zero, excess. So it's a simple technique, pretty good for small drainage basins. The Green and Amth model looks at things a little more hydrologically in detail. They look in more detail about the nature of the soils. And so they've got things like volume of the moisture deficit, the wetting front suction, the hydraulic conductivity, that's the permeability of the soils. And so I'm not going to go into any detail on that. It's easier to explain the curve number, frankly. But it's just a more sophisticated approach at looking at the hydrologic characteristics that control infiltration. Okay. Okay. So here we got our watershed, and that watershed is actually subdivided into a series of smaller watersheds. And so for computational purposes, we will typically break up the watershed into smaller watersheds and work the rainfall down. Okay, so here are those watersheds for Harris County. Again, Bray's Bayou is right about here. Okay, and so what do? Well, we need to define those sub-boundary drainage boundaries. Define the drainage divide. Okay, so what do you need for that? Well, for undeveloped areas, you basically look at the best topo maps you have. Look at historic maps. We've got maps for Harris County that go back to 1916 in 1 foot contour interval. So those are important sources of information. Aerial photos, field reconnaissance, all the things you would think of to determine that point at which the watershed goes into, or water goes into 2 different watersheds. For developed areas, it gets a little more complicated because the pattern of runoff is controlled to a large extent by roads and sewers. And the sewer lines in particular are not things we would obviously see when we look at an air photo. And so for that, you need engineering data to work that out. So reality is going to be a combination of all of these in the Harris County area. Okay, these are the things you look at, and you don't have to remember any of it, except just recognize again what we're looking at. We're looking at length of the watershed, slope of the watershed, percent urbanization, percent impervious, things like channel improvement, on-site detention. Okay, one of the roles of the Harris County Flood Control District is to provide increased or at least require on-site detention so that the water doesn't run off when you build a subdivision. You build these detention ponds, and so then you can input that into your model. Okay? Now, to get this model, to get the hydrograph, we typically use what's referred to as a unit hydrograph. And so it says for 1 unit of direct rainfall, and you could think of that as rainfall excess, okay, over the drainage area of interest at a uniform rate for a specific duration, what is the equivalent hydrograph? So let's just imagine, okay, a small drainage basin has 1 inch of rain spread over it uniformly over an hour. What would that drainage, 1 inch of rain, what would it look like if it's 1 inch of excess rain in terms of a hydrograph? Well, the assumption is that this is a linear, runoff is linear, so what it allows us to do is make simple multiples. So here is that 1 inch rainfall, and here is that runoff from 1 inch. Now, if we had 2 inches of rainfall, what would it be? Well, we'd simply stack one on top of another. So it would be that. If it was twice as long, well, we would look at adding these two together. So what we do is we add multiples of increments of rain, of units of rain. I used 1 inch, it could be 1 centimeter. I used an hour, it could be 1 minute. But it basically says that we can subdivide the hydrograph, the hyetograph, the rainfall, into increments, and then we would create a composite hydrograph by increments of the unit hydrograph. Okay. So what might we get? Well, here is the instantaneous unit hydrograph. Now what we did is we looked at the drainage basin, and this is dividing the drainage basin into, I tell you what, I'm going to have to ask the three of you to either leave right now or focus on what I'm showing, okay? Which will it be? Okay. All right. So we've got different parts of the drainage basin. And the ones farthest away, obviously, are going to take the longest time to get to the outlet. The ones closest will come immediately. So what this is the amount of water that's going to come down from A, and then from B and C and D and E. Okay. And so that's sometimes called a translation hydrograph. And then you modify it just slightly, and you get your instantaneous hydrograph. Okay. So again, we've created our unit hydrograph from a unit of rain. And then we can create the composite hydrograph from multiples of that. Now, in order to create that hydrograph, we need two things. We need a time of concentration and a storage coefficient. Okay. Now, the good news is we can determine, well, the storage coefficient and other things from measured rainfall, or rather measured basins in response to rainfall. But then we can extrapolate that to ungauged basins again. So we're always trying to calibrate our model based on where we have stream flow records and then extrapolate them. Okay. The time of concentration, the most common way, it varies depending on what you're using, is how long it takes to go from the farthest point to the outlet. That's the easiest thing to remember. Okay, so it would be the time it takes to go from here to here. That's the time of concentration. Okay, That's one definition of time concentration. The storage coefficient has to do with how long it takes for water to go down the system. And that's going to be a function of things like the ponding, of the nature of the channel. Does it flow down quickly and uniformly, or does it vary from place to place? And the larger the storage coefficient, the greater the attenuation or stretching out of that rainfall. Okay? So using these, we create that instantaneous unit hydrograph that we can then create a composite hydrograph for any rainfall we like. Okay? And so this is the basis for the discharge for the runoff hydrograph for a point in Harris County. Now, in fact, what they've done, I'll go back to this second, what they've done is they have gone one step further and used those models to route the flooding. Once we know the hydrograph at one or multiple places, we can convert that to stage, and then from stage we can route the flow to look at the elevation of the water throughout the basin. Now, the reason we do that quite clearly is in order to create floodplain maps. So I've only talked about part of the story, the flood routing part, where we look at elevation and look at how elevation changes throughout the basin, is what I'm not going to really talk about. It's just too complicated at the time we have, but it's easy to visualize, and it's easy, and it's important for you to recognize that portion of the story. Okay. Now, before we get to floodplain maps, I want to mention that we don't necessarily only want to focus on peak flows. There's a lot of reasons why we might be interested in what's referred to as flow duration. And that basically is the percent of time of that a particular discharge is equaled or exceeded. On the one hand, imagine a river that never changes its depth. It's got a constant discharge 100% of the time. So a cumulative frequency would be just a straight line. Well, that's not going to happen. Okay. Clearly, water goes up and it goes down, and so when we look at flow discharge, there is 100% of the time it's going to be greater than some real low number. Okay. And 0% of the time it's going to be greater than the biggest flow we have. So this diagram divides up intervals of time within the river from low flow to dry to mid flow to moist to high flow. Now, obviously, we tend to focus on the high flow of flooding, but there are other reasons why we might want to focus on this or on this. So let's just look and recognize that this requires a little different flow record or stream flow record. We're no longer looking at what was the biggest instantaneous peak discharge in this water year. Well, we might want to know what are the daily or monthly or annual mean discharges. So we need a completely different data set. Now the good news is we can go and get those for any gauge station, but I haven't really shown you those, but it's easy enough to imagine every day and looking at what the discharge would be. Okay, and then from this we get a annual exceedance probability, or conversely a recurrence interval for these high to low rainfall conditions. Okay, and we could do it for monthly variations as well as daily. Okay, so here's, for example, the difference in stream flow for rivers underlain by different geologic conditions. This is up in New England, and so basically The New England world is largely underlain by either glacial till, which is the material that is deposited at the base of the glacier, or stratified drift, the material that was transported by outwash and is stratified and more permeable. Okay, so the flow with material underlain by stratified drift doesn't vary much throughout the year. Okay, because there's a lot of water that is coming through the permeable till that's giving you a lot of base flow. On the other hand, look at the flow duration curve for no drift, just glacial till, which is very impermeable. It's highly flashy, and there are times when it goes dry, there's times when it floods up. Because it being impermeable, we don't have much base flow. It's essentially running off or not. So the shape of this curve depends on basically the type of material and the type of land use. So here we've got three different streams that are basically reflecting three different kinds of discharge curves. The perennial stream is basically watering all year round. So it never goes completely dry. It clearly has to have a significant component of base flow. It's going to have the lowest flow duration curve, lowest slope. Okay. The ephemeral stream, on the other hand, has zero base flow. It's peaks during parts of the time and then goes dry. It's going to have the steepest flow duration curve. Intermittent, it's really just a transition between perennial and ephemeral. And it's basically, there are seasonal periods where it's a perennial stream and seasonal periods where it's an ephemeral stream. So that might be an area like in Southern California where you have a Mediterranean climate. You've got a rainy season, in which case the streams are perennial, and then you have a dry season when they become ephemeral. Okay, and so here are how those different flow duration curves would look like depending on really the relative amount of base flow and the variability in precipitation events. Okay, so let's go back to why are we interested? Well, maybe you're interested in water quality. Okay, you'd like to know how the load of, in this case, coliform might vary. And so you've got a cumulative curve or flow exceedance where when it's below this, you're out of compliance, and when it's above it, when it's below it, you're in compliance, and when you're above it, you're out of compliance. So what you're looking at are those periods of time when the coliform is out of compliance. And interestingly enough, it tends to be during the high flow conditions. Okay, here we might look at a hydroelectric dam. Well, with the dam, it requires a certain amount of flow to get the turbines going. If the flow is too low, the turbines don't turn. So there is a low flow shutoff that says when the discharge is less than half a cubic meter per second, we have no electricity. There's also a maximum rate at which the flow turbines can go, and that basically is defined at here. Okay, so we can't get any more power than that. So we have to look at when the turbines are shut off and when they reach their maximum peak and can't be increased. So the flow duration curve is going to be used for that. If you are a fish, depending on the nature of your type of fish you are, you'd like to know whether or not this river is going to go dry, and if so, when. The variation in the duration curve has all sorts of biological implications in terms of the life cycle of the fauna and flora in rivers. So I'm focusing on the flooding, but recognize that we can also focus on different aspects of stream flow for different environmental reasons. Okay. Now, I talked about the relationship between flood frequency and flood exceedance probability, and how for certain frequencies and probabilities, we tend to use these as our guidelines for floodplain insurance. Okay, and I've already alluded to the fact that once we've got, let's say, the 1% flood, how do we transform that to the 1% floodplain? And again, that requires flood routing. For the time being, think of it as some magical device that basically transforms that for you. And when we do that, we can then get a floodplain map. This particular map, notice it's got a 1% floodplain and a 0.2% floodplain. Okay. Can anybody tell me what the recurrence interval is for a 0.2% floodplain? It's,
100 years.
no, 100-year would be
500.
this is the 500-year flood. Yeah. So when you go to buy a house, you're going to be asked, if not by the realtor, by the insurance company, is it in a floodplain? Well, you're going to go to a map like this, and you're going to see, well, it either is or isn't. And by the way, we have 3 different floodplains, one of which is the 2% or 500-year, one of which is the 1% or 100-year, and then there's something down in here that you wouldn't worry about because that's pretty much the channel. But you'd want to know this. You'd also want to know how did they make it, when did they make it, and could it be wrong? So let's think about how we make those maps first, and then we'll talk about how they might change. So here's stage A. Flow confined to the channel. We have a, let's say it's a 20-year flood that rises to a stage B. So this is the area that's flooded in that 20-year flood. And so that's going to become our 20-year floodplain. It's easy enough. Except just remember that we have this measured here. We have to be able to extrapolate the elevation upstream. Okay. Now we've got a bigger flood. It's a 100-year flood. That's the area that was flooded on that flood. And so that's the 100-year floodplain. Well, we just superimpose those. And so now we've got a floodplain map. In this particular case, it's a 20-year and a 100-year floodplain map. So the first question is, would you build, well, actually, let me just continue over to here for a second. How you would, as a planner or as a builder or as a governmental agent, decide what do we allow in those areas? Well, here's an example of one, this is from your textbook, where we've defined a floodway as the 20-year floodplain, and there's no construction allowed. Then there's the floodplain, which is between the floodway and the 100-year flood, where you can only have certain types of construction, flood-proof construction. Now, in some cases, that might just be building your house up so that the first floor, the ground floor, or the living area, is above the 100-year elevation. You have flood-proofed your construction. In other cases, there are other ways of flood-proofing the construction. So this would be a response to this type of mapping. Okay, and again, there are different regulations that can apply. Different regulatory agencies might view acceptable land uses in, say, the 100-year floodplain differently. For example, are you allowed to fill an area? If so, you need to make sure that you don't increase the flooding elsewhere. What do you do when you put a levee and basically carve out a section of the 100-year floodplain and have made it flood-proof? Okay, how do we deal with that? So these are things that you would be thinking about if you were involved in floodplain regulation, floodplain delineation. Okay? Now, as an individual trying to, or as a planner trying to decide what types of limitations might we put on development in these different zones, you might want to think about the recurrence interval over longer than a year, a 12-month period. The annual recurrence interval is really everything we've talked about so far. But consider the fact that you're going to build a house for 30 years, or you're going to build something for 50 years. Wouldn't it be a more useful piece of information to not know just the annual recurrence interval or exceedance probability, but over some period of time? So this is the equation we use, where this is the interval of time, and let's say it's a 30-year interval. So we're going to take the annual recurrence interval. Let's say it's 5 years, and we're going to take this equation, raise it to 30, and this is the recurrence interval for the 30-year, 5% flood, okay? Or 5-year, rather. So, okay, let's see what that might mean, okay? Here we've got the 10% floodplain, the 1% floodplain, and the 0.2% floodplain. So this is the chance of occurring in any 12-month period. This is your annual recurrence interval. But what about that 30 years? Well, when you plug in that formula, it turns out that in that 100-year floodplain, that's the 1% probability, there's a 26% chance you'll be flooded. So 1 in 4. That sounds different than a 100-year recurrence interval. The 10% floodplain, you got a 95%. And even in the 500-year floodplain, you've got a 6% chance of flooding during that time. So it's really important to keep in mind not only how you calculate annual exceedance probability, but also the exceedance probability over longer intervals of time. Okay. And this is part of the reason that we got problems. After one big flood, if they let me, I'll rebuild right here. I've lived here 45 years. It's never flooded. They say it's a 100-year flood. I don't guess I'll see the next one. So this is kind of the public's view of the 100-year flood, which, by the way, is why we no longer refer to it as the 100-year flood. We talk about the 1% flood. So here's an example of a 100-year floodplain map. This is at the southwest corner of Brays Bayou. Now this is a 1976 base map, okay? And that arrow points to an area where you can park. It's a park and ride. If you go to the rodeo, you can park there and get a shuttle. And I kind of like it because they've actually defined the risk. Remember, risk is magnitude times probability. The magnitude of flooding is you can have between 1.5 and almost 6 feet of water in that parking lot. The probability is it's a 100-year event. So that is the risk. So you decide, is it an acceptable level of risk? When you go to the rodeo and you park your car, you think, okay, for the period of time that I'm going to be here, am I willing to take that risk? And chances are you, and almost everybody would say yes. Okay. Now, would you build a house in that area? I would think maybe you ought to think twice. So here we've actually have informed the public about risk for a particular flood event. Okay. Herein lies one of the problems. And it starts as a question, can that 1% floodplain change with time? Because if the answer is yes, that makes it kind of awkward for you as a consumer to try to decide, or a builder or whatever, or an insurer, well, which side of that 100-year floodplain should I be on? I mean, how seriously can I really take these maps? Okay, well, unfortunately the answer is yes, but let's look at why. Well, in some cases, we just got more data. The floodplain map was based on historical stream flow data, and we've got more of it. Okay. Well, the floodplain map was based on old data under one type of land use, and the land use has changed. Or there's been structural changes. Maybe they built levees, or maybe they built a dam or detention ponds. Okay, so climate's changing. That's not a good one. So we've got all sorts of situations. I say all sorts. Here's 4 examples of how the 100-year floodplain, and better said, the 100-year flood, can change. So what it was in 1976 is not going to be the same in 2006 or 2016. Okay. So let's think about how land use changes flood frequency, or really better said, changes the magnitude of flooding of a similar probability. Because one of the problems with dealing with stream flow is that it starts with rain, and with the exception of climate change and a few other things, the probability of a rainfall event is pretty much the same. And so our first thought is the 1% rainfall generates the 1% flood. Okay, that's a good way of thinking about it. The problem is that 1% rainfall may generate different magnitudes of flooding depending on what happens to that rain as it flowing down that basin. And urbanization is the biggie. Okay, so what we've done, we've increased impervious surfaces. That results in faster drain off and shorter time lags and higher peaks. We built bridges. Those can cause backups. Storm sewers can fail or fill, and that can cause street flooding that can flood your home. Okay. We can build upstream dams or levees or flood walls or detention ponds. Maybe agricultural changes like deforestation. All of these are ways that can affect both the stream flow and the sediment discharge of a river. Okay? So let's just look at more data. This was the stage discharge relationship for an area before 1985 flood. And this is what it was afterwards. Okay? That really big flood changed the database to the point where our old predictions of what the elevation would be for a given discharge are wrong. Okay? That's not good. The impervious surface. The faster it goes from peak rainfall to peak discharge, the shorter that time lag. And here we've got this volume of water, the center of mass of runoff versus center of mass of rainfall, and let's make it run off faster. Well, by decreasing the lag time, we actually force more water through the system in a shorter period of time. That increases the peak discharge. Okay. Now, it's even worse than that, because if we were just dealing with, let's say, sewers, taking that water and very quickly getting it into the river, that's one thing. But also, a lot of the increased speed of runoff, decreased time of concentration, is because of paving. And what does paving do about the amount of excess rainfall? It increases it. So not only with no change of volume will there be an increase in peak discharge, but if we add to that the increased runoff, the increased effective or excess rainfall, then we've yet increased peak discharge again. All because we've caused impervious surfaces to increase the rate of flow and decrease infiltration. Okay. One of the ways of thinking about how urbanization might affect something is think of before and after. You're asked to do an environmental impact statement on the impact of building a subdivision on the Katy Prairie. Okay. Well, one of the questions would be how much increased rainfall, how much increased runoff rather, would there be? And so you say, okay, let's just assume that one is our before urbanization. Well, let's look at how much of that area is going to be impervious surface and sewer. 20%. Well, we've just doubled the amount of runoff. 100% sewer, by the way, you can't have more than about 60%. Wow, we've gone up to almost 6 times the normal runoff. Now, this relationship will vary depending on recurrence interval. But the fact of the matter is, we're looking at multiples of the volume of runoff, and that translates into significant increases in peak discharge in the area of flooding. Okay. Now, one of the ways of taking this kind of information is to say, okay, you're going to increase this runoff by 10,000 cubic feet. And we don't want you to. But you insist on building a house and roads. So we want you to dig a hole that will hold 10,000 cubic feet of water. So it doesn't run off and cause flooding. And we actually don't mind if you kind of let it drain slowly, because all that will do is kind of spread out the period of discharge. But we don't want it to come with the peak discharge. And that is, of course, one of the ways we use this and try to deal with flooding due to urbanization. Okay. Now, basically this is saying that the slope of this curve is a function of how much increase in rainfall there is, runoff there is with increased impervious surface. Okay. For small events, it increases a lot. Okay. With the 50-year flood or 100-year flood, it doesn't increase as much. And that's the controversial diagram, by the way. But you can argue that the effect of urbanization is less with respect to impervious surface. The effect of the impervious surface is less in a 100-year flood than it is in a small flood. And the reason is, in a 100-year flood, everything's saturated. If you've got 100% saturation, what is your infiltration capacity? It's 0. What is your CN number? It's 100. It's like open body of water. Okay, and so you've already got everything running off. Excess rainfall is pretty much rainfall. Excess runoff. Now, that's not the true with respect to the impact of the speed of the runoff, and it's not true with respect to the impact of the sewers. Okay, all that really says is the volume isn't going to be reduced very much. Okay, but when we look at running it all faster, particularly with sewers and the like, you're still going to get a significant increase due to that. So what's misleading about this is it's easy to think of this diagram as being a measure of what is the impact of urbanization. And that's not the case. It is the impact of impervious surface. And it's not the impact of the increased velocity of runoff increasing discharge. Okay. Having said that, you look at your water bill in Houston, and you're getting dinged for every bit of impervious surface that you have. The reason being is very clear that the more impervious surface you have over your lot, the less infiltration and the faster the runoff is. Okay, so here's some historical data They're the highest annual flows from 1940 to 1975. And so based on a 35-year of record, we did a plot, we extrapolated to the 100-year flood, and so this is the 100-year flood, the 1% flood. Then later, we've got more records. Now we've got 56 years of record. And look how much higher the 100-year flood and how much bigger the 100-year floodplain will be. Okay? So what might cause something like that? Well, let's look at a different set of data. Here's that 100-year flood. Oops. Here's that, a different high flood. I'm sorry. And now take a look at the shape of this compared to the shape of this. We're going to compare these in just a moment. And now look at one last set of hydrographs. Interval A, and now a new interval B. Okay. Clearly, in all three of these case studies, the 100-year flood has changed. Or better said, our estimation, our approximation of the 100-year flood has changed. And I thought I had a summary slide, so let's just look at this. In this particular one, what we're really looking at is we're getting a broader record of and sampling more of the higher events. The reality is that, you know, if we're trying to catch a 50 or 100-year event in a 35-year period of time, we probably won't. But the longer the period of time we have, the more likely we're going to get those unusual high events, and therefore the more accurate the extrapolated 100-year flood will be. Now here, it looks a little different. Yes, we're getting higher events, but look at the general flow pattern. We're also getting a lot more higher runoff in general. Okay, so here it's less likely that we're just getting more events, but rather we seem to be getting a lot more water. And so this is probably the result of something like urbanization, where we are have had some changes in this period of time from relatively unurbanized to a more urbanized basin. And here, something has happened to decrease the peak floods, probably a dam upstream. The dam is cutting off the high flow. So in all three of these cases, the best prediction of the future is not necessarily, well, in two of these cases, the best prediction of future flooding is not necessarily previous flooding. And as an example of that, let's look at Brays Bayou. Here's two hydrographs along Brays Bayou, 1949 and 1960. I say similar size storms. What I really should have said was storms of similar exceedance probability. Okay. Basically, the same rains created two different peak discharges. So 1960, the peak discharge was a lot more. And notice, it's not so much, there is actually a little more volume in 1960, but a big difference is the speed of the runoff. That rain just ran off faster and therefore higher discharge. So if we look at the peak discharges in Brays Bayou from 1930-something to 20-something, and we can look at it here, and we kind of see something, or we can look at it here. Clearly, something is going on in Brays Bayou. This is not just that we have a longer sampling period. Okay, this is a different hydrologic world. And so what is different? Well, consider what's happened in the upstream portions of Brays Bayou in the drainage basin as Houston moved west. As Houston moved west, we've completely urbanized that drainage basin. And so what was nothing but farms and ranches is now Meyerland and Westbury, etc. And so you can also see how we've changed Bray's Bayou. We've taken a little meandering bayou and we've straightened it. And why did we do that? Well, because of this. The 100-year flood was getting bigger and bigger. The annual discharge of peak floods were getting bigger and bigger. And we continue today. We're continuing to modify the channel of Bray's Bayou to deal with that increasing size. Now here's that 100-year floodplain in 1976. Here's Bel Air High School. There's the 100-year floodplain in 2007. Okay. You basically have covered all of this area. Oh, shoot. All of this area is now in the floodplain, okay, as well as some of the area. Now, what's the big difference? Well, part of it's urbanization, okay. Part of it is just better mapping. The new FEMA map is based on LIDAR mapping. So we have a much more detailed view of the topography. There's been some subsidence, not much. But basically, if you lived here in really until 2005, you were outside the official 100-year floodplain. And then the next year or two, you were in it. Now, this really upset people because their flood insurance went up. But it was simply the realization that 100-year floodplains can change with time. Okay. One of the reasons why it changed with time, I'm going to rephrase this. One of the reasons we made new floodplain maps was because of Tropical Storm Allison in 2001. And so by 2007, we had new maps. And it upset people that so much of the flooding in Tropical Storm Allison was outside the mapped 100-year floodplains. And so that's why we acquired the LIDAR data. That's why we remapped the whole area. That's also why we've been improving Bray's Bayou. That's also why we're putting in larger detention. That's also why we have new taxes on your sewer for impervious surface. All of these things were largely driven by an event, the massive flooding of Houston in Tropical Storm Allison. In fact, each of these floods precipitated major changes. And so these case studies we're going to look at are like our landslides or like our volcanic events or earthquakes, events that teach a lesson. And so I want you to look at these with that mindset in mind. And we'll start with the Black Hills flood. And the first thing is, it was a flash flood. And a flash flood means the time lag was very short. And so you had 15 inches of rainfall in 6 hours, and the water rose 14 feet in 3 hours. Okay. Hundreds of people were killed, a very large amount of damage. Basically, here's where the rain was. It was in the Black Hills, and it came down very quickly to Rapid City, which is at the base of the mountains. You got the Black Hills here, a lot of rain, and then it came down to Rapid City. Okay, so this is the hydrograph at different places. Okay, so that was not a good thing, and this is for one particular area. And when you look at it, well, first of all, wow, that was a pretty unusual event. The thought was that might have actually had a recurrence interval of maybe 500 years. We'll come back to whether or not that's true or not, but it certainly was a big flood with catastrophic consequences. Well, what the lesson learned was that there was a large number of buildings and residential areas that were in harm's way. And so they developed, because of this particular flood, what is referred to as the Greenway concept. So this is kind of the lesson learned. Most of the floodplain was converted into parks. Many of the businesses were allowed to stay there, but they were required to floodproof. All homes and motels were either leveled or moved outside the floodplain. And the fundamental concept is no one should sleep in the floodplain because you don't have time. Like Nevado del Ruiz, when you have something coming down real quickly, the time lag between knowing the event's coming and the event hitting you can be very short. And so in many other examples as well we can think of. Now that we've got a floodplain map, what do we do about it? And in the case of Rapid City, the idea was don't sleep in the floodplain. I think I'm going to stop here. We will look at 4 more floods or 4 more areas of flooding. Then we'll talk about what you can do about flooding next time. Have a good spring break. I will see you Monday week.